Hey everyone, welcome back to the channel. Today, we're diving into a super cool paper called LoRA, which stands for Low-Rank Adaptation of Large Language Models. This is all about making those massive AI models way more efficient to use. Ever wonder why fine-tuning huge language models like GPT-3 is such a pain? It's because you have to retrain billions of parameters, which costs a fortune in computing power. But what if I told you there's a way to cut down the trainable parameters by 10,000 times and slash GPU memory use by 3 times? That's exactly what LoRA does. It keeps the original model frozen and adds tiny, trainable matrices to each layer, making it super efficient without losing performance. Plus, it works great on models like Roberta and GPT-2, and there's no extra delay during inference. How awesome is that? Think about adapting a giant pre-trained language model to different tasks. Normally, you'd fine-tune it, but that means dealing with all those parameters again. For smaller models, it's manageable. But for something like GPT-3 with 175 billion parameters, it becomes a huge deployment nightmare. Why is that a problem? Because storing and running multiple fine-tuned versions is just too expensive and slow. So people have tried to fix this by only tweaking some parts of the model or adding small external modules. This way, you only need a little extra for each task, making everything way more efficient. But here's the catch. Existing methods aren't perfect, and that's where LoRA steps in to change the game. Check out this diagram. It shows how LoRA works with matrices A and B. Imagine the pre-trained weights are locked in place, and we only train these 2 small matrices to adapt the model. It's like adding a simple upgrade kit instead of rebuilding the whole engine. This figure illustrates the reparameterization trick in LoRA. By focusing only on A and B, we dramatically cut down what needs to be trained, making the process much faster and cheaper. Why does this matter? Because it lets us customize big models for specific tasks without the heavy costs. Did you know that some methods to adapt AI models actually slow them down or reduce their performance? Earlier approaches like those from Holsby and others often increase model depth or limit sequence length, which can cause delays and fail to match the quality of full fine-tuning. This creates a tricky trade-off where you sacrifice efficiency for better results or vice versa. Here's a cool idea inspired by research showing that over-parameterized models live in a low-dimensional space. We think the weight changes during adaptation also have a low intrinsic rank, leading to our method called Low-Rank Adaptation, or LoRA. Instead of training all the model weights, we only optimize small rank decomposition matrices while keeping the original model frozen. For a huge model like GPT-3 with 175 billion parameters, using a very low rank of just 1 or 2 works amazingly well, making LoRA super efficient in storage and computation without losing performance. Imagine having one pre-trained model that you can reuse for many tasks by just swapping out tiny LoRA modules. You freeze the big model and switch tasks by changing small matrices A and B, which cuts down storage and makes task switching a breeze. LoRA also speeds up training and lowers hardware costs by up to 3 times because you don't need to handle gradients for most parameters, only the small injected matrices. Plus, when you deploy it, you can merge these matrices back in with no extra delay. And it works well with other methods like prefix tuning for even more flexibility. Let's get familiar with some terms from the transformer architecture. We talk about input and output dimensions, and matrices for queries, keys, values, and outputs in the self-attention part. The pre-trained weights are fixed, and we use a rank R for LoRA modules. Following standard practices, we optimize with Atom and have a feed-forward dimension that's 4 times the model dimension to keep things efficient. Now, let's dive into the problem we're solving. Although LoRA can work with any training goal, we're focusing on language modeling. This is all about maximizing conditional probabilities based on specific prompts for tasks like summarization or converting natural language to SQL. Picture this. You have a pre-trained language model, say something like GPT, built on the transformer. We want to adapt it for tasks where you give it a context and it generates a target, like turning a question into a SQL command or summarizing an article. Each task has its own data set of these pairs, and the goal is to tweak the model to handle them better without starting from scratch. Ever wondered how fine-tuning a giant AI model actually works? It starts with the pre-trained model's weights, and then we tweak them step by step using gradients to make the model better at specific tasks like writing or summarizing. But here's the catch. Every time you fine-tune for a new task, you end up with a whole new set of parameters. Imagine if you had to store a separate copy of GPT-3 for each job. That's 175 billion parameters multiplied by the number of tasks. It's totally impractical and eats up tons of storage and memory. So what if we could be smarter about this? Instead of changing all those parameters, we use a much smaller set to encode the updates. This way, we're optimizing just a tiny fraction, making the whole process way more efficient without losing performance. In the next parts, we'll dive into how LoRA uses low-rank matrices to pull this off. Think of it like adding a small, efficient upgrade module instead of rebuilding the whole engine. For a massive model like GPT-3, this cuts trainable parameters down to just 0.01% of the original. Now that's a game changer for speed and cost. Are the current methods for adapting AI models really up to snuff? Over the years, researchers have tried all sorts of tricks to make fine-tuning cheaper and faster. Two popular approaches are adding adapter layers or tweaking the input prompts, but both have big downsides in real-world use. Let's talk about adapter layers first. They're like little extra modules squeezed into the model, but even though they're small, they force the system to process things step by step instead of all at once. In online scenarios where you're handling one request at a time, this sequential processing can really slow things down. For example, on a single GPU with a model like GPT-2, you'll see a noticeable lag as shown in the paper's table because the hardware can't parallelize the work as effectively. This latency issue gets even worse when you split the model across multiple GPUs. The extra layers mean more coordination between GPUs, which adds delays unless you duplicate the adapter data, wasting resources. Now, what about optimizing prompts directly? It sounds neat, but it's tricky to get right. The performance doesn't improve smoothly as you add more parameters. And by reserving part of the input for tuning, you have less space for the actual task. This often leads to worse results compared to other methods, and we'll explore those performance details later in the paper.
We are Genipad. Your likes and subscriptions inspire us to create more videos and keep improving our service. Want to turn your own content into videos? Visit us at www.genipad.com.
Ever wondered how much faster LoRA is compared to other methods? This table shows inference latency in milliseconds for different batch sizes and sequence lengths. LoRA consistently has lower latency, meaning it's faster for real-time applications. For example, with a sequence length of 128, LoRA is about 20% faster than adapter layers, which is huge for online services where every millisecond counts. This table compares inference latency for GPT-2 medium, and LoRA wins by having no extra delay, while adapters add significant slowdowns. The key takeaway is that LoRA avoids the latency issues that plague other tuning methods, making it ideal for scenarios with short sequences, like chatbots or quick queries. Let's dive into how LoRA actually works. It's super simple. and brings big practical benefits. Think of it as a way to tweak any deep learning model efficiently, though we're focusing on language models here. The idea is to make small, smart updates without overhauling the whole system, saving time and resources. Did you know that neural networks have layers with full rank matrices? But when adapting to tasks, the changes needed are actually low rank? That means we can represent updates with small matrices B and A, where B is initialized to 0 and A starts randomly. This keeps the original weights frozen, so you're only training a tiny fraction of parameters, making it super efficient. In the forward pass, the input goes through the original weights and a low-rank update, and their outputs are added together. This ensures the model behaves as if it's fully fine-tuned, but with way less computation. To make training stable, we scale the update by a factor alpha, which acts like a learning rate. By setting alpha based on the rank, we avoid tedious hyperparameter tuning, so you can focus on getting results fast without getting bogged down in settings. LoRA is like a flexible version of full fine-tuning. If you use it on all layers and increase the rank, it can match the performance of training the entire model. Unlike adapters that limit the model or prefix methods that restrict inputs, LoRA scales up smoothly, giving you the best of both worlds, efficiency and power. Here's the best part. LoRA adds no extra delay during inference. You can combine the small matrices with the original weights beforehand, so deployment is as fast as using the base model. Need to switch tasks? Just swap out the small modules quickly, with minimal memory use, making it perfect for dynamic environments. So here's the cool part. LoRA is designed so that when you're actually using the model after training, there's no extra delay at all compared to a fully fine-tuned model. It's built right into the method to keep things super fast. Now, let's dive into how LoRA works with transformers. You know transformers have those attention layers with weight matrices for queries, keys, and values, plus MLP layers. LoRA focuses on just the attention weights for fine-tuning, leaving the MLP parts frozen. This makes it simpler and saves a ton of parameters. They're not touching the MLP or other layers here, but maybe future research will explore that. The practical benefits are huge. Imagine cutting your GPU memory usage by 2/3 during training. For a giant model like GPT-3, that means going from over a terabyte down to just 350 gigabytes. Storage shrinks massively too, by about 10,000 times, so you can switch tasks on the fly without reloading everything. Training speeds up by 25% because you're not calculating gradients for most parameters. It's like having a super efficient toolkit for customizing AI models without the usual bottlenecks. But LoRA isn't perfect. One limitation is batching inputs for different tasks. If you merge the LoRA weights to avoid latency, it's tricky to handle multiple tasks in one go. However, if speed isn't critical, you can keep the weights separate and pick the right modules dynamically. All right, let's talk experiments. They tested LoRA on models like Roberta, Deberta, GPT-2, and even scaled up to GPT-3. They covered everything from understanding language to generating text using benchmarks like GLUE and tasks like converting natural language to SQL or summarizing conversations. All this was done on NVIDIA GPUs to see how well LoRA performs in real-world scenarios. For baselines, they compared LoRA to other methods by replicating setups from earlier work. This means some baselines only show up in specific experiments, but it helps keep things fair and consistent. Full fine-tuning is the standard approach where you update all the model's parameters. A simpler version just tweaks the last few layers while freezing the rest. They included one such baseline from prior research on GPT-2 to see how LoRA stacks up. Ever wondered how different fine-tuning methods stack up in real-world tests? This table compares LoRA with other approaches like full fine-tuning and adapters on tasks like language understanding and sentiment analysis. For example, raw database with LoRA uses only 0.3 million parameters, but achieves scores close to or better than full fine-tuning, which needs 125 million parameters. That's a huge efficiency gain, showing LoRA delivers top performance without the heavy resource use. In tasks like MNLI and SST2, LoRA often matches or beats other methods, proving it's a smart choice for adapting models quickly and effectively. This table is all about evaluating methods on the GLUE benchmark, where higher scores mean better performance. It uses accuracy for most tasks, Matthews correlation for COLA, and Pearson correlation for STSB. The asterisks and symbols indicate data from prior studies, ensuring fair comparisons. So when you see LoRA outperforming others here, it's not just a fluke. It's backed by rigorous testing across multiple models and setups. Let's talk about a simple baseline called bias only, or bitfit. Here, only the bias vectors in the model are trained, while everything else stays frozen. It's like tweaking just the fine-tuning knobs, without touching the main machinery. This method was explored in bitfit by Zakin et al. In 2021, and it's super lightweight, but often doesn't capture complex changes needed for top performance. What if you could add special trainable tokens to your prompts? That's prefix embedding tuning, or pre-embed. You insert these tokens at the start or middle of your input, and they learn to guide the model's responses. The placement matters a lot. Prefixing adds them at the beginning, while infixing puts them elsewhere. The number of trainable parameters depends on how many tokens you add, and the model's size, making it flexible but sometimes tricky to optimize. Now level up with prefix layer tuning, or pre-layer. Instead of just training token embeddings, this method learns activations after every transformer layer. Imagine replacing parts of the model's internal computations with customizable blocks. It uses more parameters because it covers all layers, allowing deeper adjustments but at a higher cost compared to simpler methods. Adapter tuning inserts small adapter layers into the model, like adding extra modules between attention and MLP parts. These adapters have fully connected layers with nonlinearities to learn task-specific changes. Over time, designs evolved for efficiency. Some put adapters only after MLP layers or use layer norm to save resources. Variants like adapter drop skip some layers to speed things up. The trainable parameters grow with the number of adapter layers and model dimensions, balancing performance and overhead. So how does LoRA actually work? It adds pairs of low-rank matrices in parallel to existing weights, focusing on key parts like the query and value matrices in attention layers. This means you're only training a tiny fraction of parameters, determined by the rank and the original weight shapes. For instance, if the rank is small, you get massive savings in parameters without losing effectiveness, making it ideal for quick adaptations. Ever wondered how different fine-tuning methods stack up in real-world tests? This table compares GPT-2 models with various adaptation techniques on the EasyE NLG challenge, using metrics like BLU and Rouge-L, where higher scores mean better performance. LoRA, with only a tiny fraction of trainable parameters, often beats or matches other methods, showing it's not just efficient, but highly effective. For example, LoRA on GPT-2 Large achieves top scores in several metrics, proving that small, smart updates can deliver big results without the heavy computational load. This summary highlights that LoRA consistently outperforms baselines like adapter layers and prefix tuning even with fewer parameters. Confidence intervals from experiments confirm its reliability, making it a standout choice for tasks where efficiency and performance matter. Roberta is a refined version of BERT that boosted performance without adding many parameters, and it's still widely used despite newer models. In this experiment, LoRA is tested against other methods on glue benchmark tasks with adjustments to ensure a fair comparison, like using the same batch size and initializing from the pre-trained model. This setup mimics real-world conditions, showing LoRa's adaptability and how it holds up against established techniques. DeBerta is a powerful BERT variant trained on massive data, excelling in benchmarks. Here, LoRA is evaluated to see if it can keep up with full fine-tuning on DeBerta XXL for glue tasks. The results, detailed in the table, demonstrate LoRa's ability to match top performance even on large, advanced models, reinforcing its versatility across different model architectures. After proving LoRa on language understanding tasks, does it work for language generation models like GPT-2? This section focuses on the EZE-NLG challenge, with results showing LoRa's success in text generation. Due to space limits, only key findings are highlighted here, but it confirms LoRa's edge in NLG, backed by consistent hyperparameters and comparisons to other datasets. Ever wondered how LoRa stacks up against other fine-tuning methods on a massive model like GPT-3 with 175 billion parameters? In this table, we see LoRa using only 4.7 million trainable parameters, which is super tiny, and it still beats full fine-tuning on tasks like Wiki SQL, multi-NLI matched, and SAMSUM. For example, on Wiki SQL, LoRa gets a slight accuracy boost, and on SAMSUM, it improves those Rouge scores for text generation. This shows that LoRa isn't just efficient, it actually performs better, making it a game changer for adapting huge models without the usual costs. Now, let's talk about scaling up to GPT-3 with 175 billion parameters. Testing LoRa on such a giant model is like the ultimate challenge, because training costs are sky high. To keep things practical, the researchers didn't run tons of repeats, but focused on typical performance variations. They used specific settings for hyperparameters, which you can check in the appendix for all the nerdy details. Here's the exciting part. LoRa not only matches, but often exceeds full fine-tuning across all datasets. But wait, there's a twist. Some methods don't get better just by adding more parameters. For instance, if you use too many tokens in prefix-based methods, performance actually drops. Why? It's probably because the input data starts to look too different from what the model learned originally, messing with its predictions. The team also looked at how these methods handle low data situations, which we'll dive into later. Check out this graph comparing different adaptation methods. As the number of trainable parameters increases, LoRa shows better scalability and task performance on Wiki SQL and MNLI matched. It means LoRa grows more effectively without hitting performance walls, unlike others that might struggle. This visual really highlights why LoRa is so robust for real-world applications. This figure plots validation accuracy against the number of trainable parameters for GPT-3 on Wiki SQL and MNLI matched tasks. LoRa stands out by scaling smoothly and delivering top performance, while other methods like prefix tuning or adapters might plateau or decline. It's a clear win for LoRa in handling big models efficiently. Definitely something to get hyped about for anyone working with AI. Let's take a quick detour into the history of transformer language models. The transformer architecture, introduced in 2017, revolutionized NLP with its self-attention mechanism, allowing models to focus on different parts of input sequences. Then, models like BERT and GPT-2 built on this, using large-scale pre-training to dominate tasks. Think of it as the foundation that made today's AI chatbots and translators possible, setting the stage for methods like LoRA to fine-tune them efficiently. Did you know that fine-tuning large language models on specific tasks can boost their performance way more than just training them from scratch on that data? It's like taking a genius who knows everything and giving them a quick crash course to become an expert in one area. For example, GPT-3, with its massive 175 billion parameters, is the biggest transformer model out there, and fine-tuning it helps it adapt better to things like answering questions or writing stories. Now let's talk about prompt engineering versus fine-tuning. With GPT-3, you can tweak its behavior by crafting the perfect prompt, but it's a bit of a guessing game that requires a lot of trial and error. On the other hand, fine-tuning retrains the model on specific tasks, which often means updating all its parameters for the best results. But here's the catch. For a giant like GPT-3, this is super expensive and needs tons of GPU memory, making it hard for most people to do. Ever wondered how to make model adaptation faster without slowing things down? Some methods add extra layers called adapters between the model's existing layers, but they can cause delays during inference because they add extra steps. Our approach, LoRA, uses a similar idea but with a twist. It applies small, low-rank updates that can be merged back into the model before inference, so there's no lag. Think of it like adding a quick software patch that integrates seamlessly, unlike adapters that might need extra processing time. There are other tricks like optimizing input embeddings, but they eat up space in the prompt, limiting what you can do. LoRA avoids that and could be combined with other methods in the future for even better efficiency. Why do low-rank structures pop up so often in deep learning? It turns out many machine learning problems have an inherent simplicity, like how a complex image can be described with just a few key features. Over-parameterized neural networks often end up with low-rank properties after training, meaning they don't need all their complexity to work well. Some researchers even force low-rank constraints during training to save resources. Theoretically, neural networks excel when the underlying tasks have this low-rank nature, and it can even help in areas like adversarial training. So using low-rank updates for adaptation isn't just efficient, it's backed by solid research. Since LoRA works so well, let's dive into why these low-rank updates are so powerful. They not only make it cheaper to run experiments by reducing hardware needs, but also make it easier to understand how the updates relate to the original model. For instance, with GPT-3's huge size, LoRA cuts the trainable parameters by 10,000 times without hurting performance, which is like trimming a massive library down to a few essential books. We did a bunch of tests to figure out which parts of the transformer model are best to adapt when we're limited on parameters. It's like deciding which gears in a complex machine to tweak for maximum effect without overcomplicating things. Ever wondered how to make pre-trained language models work better for specific tasks without reinventing the wheel? The authors dive into key questions about the low-rank adaptation matrix, like whether it's truly ranked efficient and how it relates to the original weights. They believe answering these sheds light on the core principles of adapting models efficiently, which is a game changer in natural language processing. So which parts of the transformer should we tweak with LoRA to get the best bang for our buck? With a tight parameter budget, the focus is on the self-attention module. For a massive model like GPT-3 with 175 billion parameters, they allocated a small budget of 18 million trainable parameters. This means using a rank of 8 if adapting one type of attention weight, or rank 4 for 2 types across all layers, and the results are eye-opening. The table shows validation accuracy on tasks like Wiki SQL and multi-NLI. Adapting different weight types like WQ, WK, WV, and WO reveals that combining WQ and WV gives the highest scores, around 73.7 for Wiki SQL and 91.7 for multi-NLI. This isn't just random. It tells us that spreading the adaptation across more matrices with a lower rank works better than focusing on one with a higher rank. Why does this matter? Well, putting all parameters into just WQ or WK leads to worse performance, but adapting both WQ and WV with a rank as low as 4 captures enough information to outperform others. It's like using multiple small tools instead of one big hammer, more efficient and effective for the job. Now, what's the magic number for the rank in LoRA? The authors tested different ranks while adapting combinations like WQ and WV, or all attention weights, to see how it affects performance on tasks like Wiki SQL and multi-NLI. The results in the table are surprising. For adapting WQ and WV, even a rank of 1 gives strong accuracy, like 73.4 for Wiki SQL and 91.3 for multi-NLI, and it doesn't improve much with higher ranks. But if you only adapt WQ, you need a larger rank to compete. This hints that the weight matrices have a very low intrinsic rank, meaning small updates are all you need. This finding is huge. It shows that LoRA works well with tiny ranks, especially when adapting multiple weight types. The authors checked if higher ranks add meaningful subspaces and found they don't, reinforcing that low rank is sufficient. It's like discovering that a simple key can unlock a complex door, saving time and resources. Ever wondered how these tiny adaptation matrices in LoRA actually learn similar things, even with different ranks? The researchers compared matrices with rank 8 and 64 from the same pre-trained model. They used a technique called singular value decomposition to break them down into their core directions. Then, they measured how much the top directions from the smaller rank matrix overlap with those from the larger one. This overlap score ranges from 0 to 1, where 1 means they're perfectly aligned and 0 means completely different. It's like checking if 2 different-sized toolkits share the most essential tools for a job. This overlap score is calculated by looking at the top singular vectors from each matrix. Think of it as comparing the most important features they both capture, ensuring we're focusing on what really matters. The results show that this overlap varies depending on which directions you compare, and they visualized this in a figure. They focused on one layer of the model for simplicity, but the findings apply broadly across all layers, as confirmed in other parts of the paper. Check out Figure 3. It shows how the top directions in the adaptation matrices for different ranks overlap. For both the query and value weight updates, the highest ranked directions are almost identical between the rank 8 and 64 matrices. The smaller plots zoom in to highlight that lower ranked directions don't match as well. This tells us that the most critical learning happens in those top singular vectors, making low-rank adaptation super efficient. Here's the big takeaway from that figure. The top singular vectors from the rank 8 and 64 matrices overlap a lot, especially for the first direction. In fact, for the value weights, they share about half of their subspace, which explains why using just rank 1 works so well in tasks like those with GPT-3. It means the model is learning the same essential adjustments, and the rest might just be noise from training. Since both matrices come from the same pre-trained model, this overlap proves that the most useful directions are consistent. The other directions could be random noise picked up during training. That's why LoRA can get away with such a low rank. It's capturing the core changes without the fluff, making adaptation incredibly efficient. What if we run the same experiment with different random starting points? The researchers did that with rank 64 and found that the query weight matrices share more common directions across runs compared to the value weights. This suggests that query weights have a higher intrinsic rank, meaning they need more complexity to adapt properly. In contrast, value weights are simpler. When they compared this to random matrices which share no common directions, it confirms that LoRA is learning meaningful patterns, not just noise. Now, let's dig into how the adaptation matrix relates to the original weights. Does it align with the most important directions of the pre-trained model? In other words, is the update focusing on the key features that the model already uses? This could explain why LoRA is so effective without messing with the core structure. Ever wondered how LoRA's tiny updates actually work inside the model? In Figure 4, they're comparing the similarity between adaptation matrices from different random starts. For the query and value weights in a specific layer, the heat maps show that the top directions align closely, meaning LoRA consistently learns the same important patterns, unlike random noise. This tells us that LoRA isn't just making random changes. It's honing in on key features that matter for the task, which is why it's so efficient and reliable. To dig deeper, the researchers projected the original model weights onto the subspace defined by LoRA's updates. By comparing norms, they could see how much LoRA amplifies certain directions in the weights. This isn't just random tweaking. It's like finding hidden gems in the pre-trained model and turning up their volume for specific tasks, which explains why such small changes can have a big impact without messing up what the model already knows. Table 7 breaks down the norms for different matrices in GPT-3's layers. It shows how LoRA's adaptation matrices compare to the original weights and random ones, giving us a clear picture of where the magic happens. What do we learn from this table? First, LoRA's updates are closely tied to the original model weights, not random noise, so it's building on what's already there. Second, instead of just repeating the top features, LoRA boosts the ones that were underused in pre-training. And third, the amplification is massive. For a low rank, it's like multiplying the effect by over 20 times. This means LoRA efficiently highlights task-specific features without needing a full overhaul, saving tons of resources while keeping performance sharp. So, what's the big takeaway? Fine-tuning giant models like GPT-3 used to be a nightmare, super expensive and clunky for switching tasks. But LoRA changes the game by making it cheap and fast, with no slowdowns during inference. You can swap tasks on the fly by just changing tiny modules, and it works not just for transformers, but potentially any neural network with dense layers. How cool is that for real-world apps? Looking ahead, there's so much more to explore. LoRA could team up with other efficient methods for even bigger gains, and the real mystery: how do models adapt their pre-trained knowledge to new tasks? LoRA makes this easier to study than full fine-tuning, opening doors to smarter AI that learns faster and cheaper.